This is Further Mechanics 2 from 2019. Let's do question number 1. So we've got a hemisphere here that's kind of hollowed out, and you've got a mass running around the middle in a circle. So it's one of those circular motion questions. Let's put some forces and stuff in the picture. First, though, I can work out the radius of the circle that it's travelling through just by doing a bit of Pythagoras. That distance is obviously a, because it's the same as that distance, right? It's the radius of the hemisphere. This distance is a quarter a, just because it's the same as this, and therefore Pythagoras tells me what this distance is. If I just do this one squared minus this one squared square rooted, I'll get this. Square root of 16 is 4, and then square root of a squared is a, and square root of 15 is square root of 15. Good, so that's that, root 15 over 4a. And now we can put in some forces. So we've got mg obviously going straight down. We've got a reaction force going straight perpendicular to the contact with the bowl. So yeah, that's good. And now we can resolve forces up and down and left and right. Up and down we have r, if we call this maybe up here theta, or alpha, maybe I should say instead, because I apparently labelled it alpha. We've got that r cos alpha is going upwards, right? Because just to be clear, maybe you could say this is an alternate angle here. So alpha is here, so therefore this is next to the angle, so it's adjacent, so it's cos. This is r cos alpha. You could also say that this angle here is 90 minus alpha, and then therefore this is sine of 90 minus alpha, which is the same as cos of alpha. That relationship will come in handy a couple of times in this paper maybe. But anyway, this is r cos alpha, which equals mg, just resolving up and down. And of course, resolving left and right, our sine alpha, therefore going this way, will be equal to, well, actually, there's no forces going the other way, but we can do F equals ma. We can say the force going towards the centre is r sine alpha equals m times the acceleration towards the centre, which is given by omega squared a, where a is the radius, which in this case is this, and omega squared r is the radius, which is this in terms of a. And then, of course, we can solve both these things, right? Because we actually know something about alpha. We can say, for example, cos of alpha is a quarter a over a, which is just a quarter, and sine of alpha is this over a, which is just this, without the a. And we can put those both in, right? So if that's a quarter, we can times over by 4 to get that. And we can put that into there. We can also put the sine of alpha result we have in there. And we can solve this for omega eventually. And we'll have that. So that's 6 marks picked up. So that's nice. Question number 2 is the F equals ma question, except it's F equals ma where we have we're looking for x. So instead of using F equals ma, we use F equals mv dv by dx. The other one is F equals m dv by dt, which we'll use later on. But you just need to know both of those. So this here, then we have a force of k over v going in the same direction as the thing. We have a mass of 0.4, so we're just going to put that in. This is a differential equation we can solve times everything by v times everything by dx. We get this. We can integrate both sides of this to get kx and 0.4 over 3. Now 0.4 is 4 tenths, over 3 is 4 30ths, v cubed, and then there's a plus c. We're given some initial conditions which will help us to find k and c. If we put in these two values into here, we get this. If we put in these two values into here, we get this. Just doing this all in the calculator. Do this, take away this, you get this. Again in the calculator, divide by 3 and you get this. Put that into one of these two things, it doesn't matter, and you eventually end up with that. So our equation from here, using k and c that we've just found, looks like this. We can of course rearrange that, and I think I times everything by 180 here to get this. And then you can just, of course, rearrange it and you get exactly what they wanted. The time taken for p to increase from here to here. So now we want to use the formula F equals m dv by dt, because we're talking about time now. So again, F is just k over v still, m is still 0.4. This is another simultaneous equation. K we know to be 61 over 180, so I can replace that in there like this. Again, a differential equation here, times everything by v times everything by dt. Pretending this is a fraction, I guess. I'm contractually obliged as a mathematician to tell you that it's not, but who cares? And we get this. We can of course integrate both sides very, very easily. We get this. We can. You could do a definite integral here with these two numbers. I tend not to. I don't really know why. I tend to just put in the value of v is 2 into here and find the first time, which is divide by 61, you get this over 61 for the first time. Then put in v as this, and you find the second time, and the time between the two is just t2 minus t1, which is this minus this, both with divided by 61s in them, which actually don't matter at all, really, do they? The c's cancel, of course. This minus this is 81, and you end up with this here, and we'll have question 2 done. Question 3 is the first centre of mass question on this paper. So we need to know the formula for y bar. If you're doing an integral like this, it's going to be this formula here, not given in the formula book, so you need to know this. What they tend to do is they tend to give you the area of this, which is of course this bit, just the integral between 0 and 4 of the function itself. So that's just 8 there, which is helpful to know. It just saves us doing a bit of calculation. Now a half y squared, I didn't bother writing this down, but y squared is this whole thing times itself. So imagine putting a bracket here and then writing it again. You're going to expand brackets. So it's going to be this times itself, which is the 16th x minus 2 to the 6. And there's going to be this times 2 plus another this times 2. Now this times 2 is a half, and then another one makes just a whole copy of that. And then of course 2 times 2 gives you 4. And so that's just this expanded out. I've brought the half out to the front because obviously it doesn't matter in the integral. And now I can just integrate this. Just be very careful, I guess, to do it correctly. When it says this, maybe just set out some working, just spend the extra minute writing the working down, I guess. There should be a closed bracket there. I guess I've forgotten to write it, but who cares. Some stuff cancels here. This cancels with this, which is nice. And so we just end up with this plus a copy of itself plus this over 16. Eventually that goes in the calculator and ends up being this, which is good. So that's y bar. Now we're going to suspend this from A, which means we, it's going to obviously hang through the center of mass, which means we also need x bar. The formula for x bar is this, slightly different formula to this. You just do x, y on the top, same down here. So this is still 8 down here. This is easier to get because we just times this by x to get this. Now, there's much more intelligent things to do than what I did here, but I just expanded this out binomially. You can check my maths if you want to, and also put the x in there as well. Nicely, the quarter of that makes 2x, and that cancels with that, which is quite cool. So we end up with this integrated. We put the 4 and the 0 in, and eventually you end up with this. I've been less careful with this one because it doesn't say, well, I guess it actually does say that I'm still not allowed to do this. But anyway, put those in and you get this. It's not too hard. And yeah, so we have a point here, which is 2.4 across and 8/7 up. And when we hang from A, it's going to hang from there through the center of mass. And we're looking for this angle here, theta. Now, of course, all I have to do is work out this length and this length. Now, firstly, this length across here, if that's 2.4 there to the center of mass, and this whole distance is 4, 4 minus 2.4 is 1.6. And then this thing here, well, that up there, we're actually told is at 4. And this is 8/7 up. So this here is 4 minus 8/7, which is 28/7, minus 8/7, which is 20/7. And then we can just do tan inverse of this over this, and we'll end up with our answer. Question number 4 then, another center of mass question back to back, a slightly different one this time. We have a non-uniform thing. So to find the total mass, which is the first question, there it is, sorry, find the total mass of the flag barrel, you just integrate this for how long it is. So you integrate this between 0 and 4, and that will find the total mass, which is essentially just this, and we'll have 48, so you can work through the working there if you want to. Next, it's hanging on a thing, so let's put in a bunch of forces. So we're going to have a reaction force here, which actually doesn't end up mattering. We're going to have a tension force, obviously, here holding the thing up. We're going to have an mg coming down here, and we're also going to have an mg coming down from somewhere on this flagpole. We need to find how far along the center of mass is so that we can model that. So okay, to do that, we're going to do a very similar integration, but we're going to integrate and also multiply by an x. Again, this is just things that you just need to know how to do because none of it's given in the formula book. But to find the center of mass here, you do the same sort of integral, but with an x in there. I'll show you the formula in a second to get this. And now essentially you're doing sort of this again, where you've got the total. You can think of this as the total mass because that's what we did before. I'm sort of imagining y to be y equals this thing. So it's sort of essentially this formula here where you have, which we actually saw in the previous question, didn't we? Where it's x times the formula integrated and then just the regular thing down there. So it's the same kind of idea. I've already worked out that this top bit is 80, this bottom bit is 48, as already worked out as well. And so we end up with this cleans up to that. So 5/3 away from A, we have our center of mass, which is just less than 2, I guess. And 2 is halfway along, isn't it, where this is linked there. So we have 5/3 of the way along there. We have an mg coming down, m being 48. So okay, now we can just take moments around A. I think because if we say, well, okay, if this is 45, then I think this is 45 as well, just based on, well, I guess, well, that's 45 there. And then, what's the easiest way of thinking about this? Oh, sorry, that's 45 there, isn't it, because of alternate. and then this is 90, so that's also 45. So if this is 45, this is next to it, so this is 45, either cos or sine 45. I must have thought about it a different way to get it the first time. It's obviously not going to matter. 45 is equal to sine and cos. Now here we also have, we can do it the same, it's just 48g sine 45 again, because it's just going in the same direction. And now we can take moments, right? We can do 5/3 times this, plus 4 times this, equals 2 times this, going anti-clockwise the other way. So I think that will be our formula here. Of course, sine 45 is just 1 over root 2. You can just type this straight into a calculator if you want to, and you'll end up with this to 2 significant figures, because I used g as 9.8, which is also 2 significant figures. So I just got to there. And that's the tension, and then give a reason this is not likely the true value. Just come up with anything sensible. So for example, up here it says that the cable itself is modeled as light. I think it says somewhere, yeah, as a light and extensible. That's unrealistic, right? It would actually have a mass that's acting down that would mess up your calculations. It also would extend and hold, it would extend, and therefore the tension would be also messed up a little bit as well. This has been modeled as a particle, whereas in fact if it was actually a mass, then its center of mass itself would have to be worked out and be slightly different to where we put it. Lots of things you could say. Anyway, moving on to question 5, which is another center of mass question. I think it's the third one in a row. I think it's the only last one on the paper. But third center of mass question in a row. This time it's about a volume of revolution. So there's another different formula we just have to know, which is this one here, which is the center of mass, the y bar, essentially center of mass, so the distance from the origin, the center of mass of the shape here is given by this formula, where v is the volume, so that's just your regular volume of revolution going around this, which you worked out in obviously Corpuscle 1 or whatever it was. However, it usually gives you that, just like it did in the previous question, and then we just need to know this bit that we put on top. So again, this is just a formula that needs memorizing. Of course, we replace the x squareds here because we're integrating with respect to y. So x squared is, where if you square all this, you get y to the 4 equals 4x squared. Divide by 4, and you end up with x squared is a quarter y to the 4. Now I've moved this volume over to here and put it there, just because that makes me, I can write more lines now because I'm taking up less space. That's just why I've done that. Anyway, like I said, this is a quarter y to the 4. You can multiply those things, bring the quarter out. You can just do some integration here. It's not complicated. And then you can cancel the pi's, times by 5, divide by 8, which cancels with this mostly, and then with this. And I think you end up with this eventually, which is 5/3 the way up from the origin. 2 minus 5/3 is 1/3, and so it's 1/3 away from the plane face. When you rotate this round, you'll end up with a flat face on top. So 2 minus 5/3, it gives you 1/3 from the top. Good. Next, we're going to take that shape here. We're going to attach a cylinder on top of it and turn it upside down, so we end up with this. So a couple of things going on here. We've got two centers of mass. We've got one of them, which we know is a third up from here, because it was a third down from there, so it's a third up from here. Plus 4 makes 13 thirds up to here. And then the center of mass of the cylinder, of course, is just, because it's a uniform cylinder, I think it says somewhere, is just 2 up from here. So now we just need to work out the center of mass of this whole shape would be our next step. Now the slight difficulty here is that this shape is much more dense than this one. So we need to think about the volumes first. The volume of the cylinder is obviously just 2 pi r squared, pi r squared where r is 2, so pi times 2 squared, which is 4 pi, times this distance of 4, so that's 16 pi. The volume of this, they already told us, was that. Now, usually to combine these center of masses, we would do total volume times, center of mass equals this center of the position of this center of mass away times the volume of this, plus position of this times the volume of that. However, I'm going to make so that's basically what I've done, but I'm going to make one slight adjustment here, which is I'm going to times this by 3 because it's 3 times as dense. So, usually I'll just put 8/5 here and 8/5 here, and this would be total volume equals distance from this one to this one times the volume of this one, and then distance from here to here times the volume of this one, but I've times both of those by 3 because it's 3 times as dense. I can just sort this out now, the pi's all just cancel, which is nice. You can type it into a calculator, you end up with this. So that's the distance of the center of mass up from the bomb. And so now, what we're being told is being put on a inclined plane, angle theta, and it's on the point of toppling. The plane is very rough, so it's never going to slip. So we end up with a picture being like this. We found that the center of mass, this whole shape is 33/13 up. And now what we need is the vertical line coming down from here. We need it to be right on this edge. So I've drawn the picture very roughly, but essentially I need this length. Of course, the radius of the cylinder is 2. I want that length there to be 2, because I want to raise this theta so far that this comes straight down to be there. And I want this length, therefore, to be 2. So I just find for what value of tan theta is tan theta 2 over this. We do to inverse tan, and we end up with this angle here. Okay, so question number 6 is, finally we're done with centre of mass. We've got simple harmonic motion this time. A and B are 4.5 meters apart. We've got a string that's natural length 1.5, so it's already being stretched quite a lot just to fit here. This is the formula for the tension. We learned that in FM1, I believe. Whenever the string is attached, a particle, is attached, so that AP is 1.5. So a particle is attached here. And now what you've done, therefore, is you've split the string into the ratio 1 to 2. And so, like, the natural length of this part of it should be a third of this. So the natural length of this part of the string is, a third of this. So this part of the string wants to be 0.5 long, and this part of the string wants to be 1 meter long, because you split it in the ratio 1 to 2, and it's sort of being shared equally. And anyway, that will come in handy later. So we've got the mass there, and we're going to obviously use F equals mx double dot, so that we can show simple harmonic motion. This is being pulled, how far along? It's being pulled another 0.5 meters along. So the amplitude is going to be 0.5. That's going to be helpful later. And if we imagine this has just moved a little distance x along here, we can set up a couple of formulas here. We've got tension going this way, obviously, so when we move this along, there'll be a tension in this string pulling it this way, because this string is still being stretched, right? And we've also got a tension in this part of the string. We're kind of imagining it's two different strings now, going this way. And we'll set up F is obviously T2 minus T1. If we imagine it being pulled, being in a position a little bit away from here, the acceleration will be coming towards the center, because the acceleration is always towards the center. So if we imagine x to be positive in this direction, the acceleration will be negative going this way. Now T1 and T2 we can use these formulas for. Lambda is 15. I talked about the natural length. The natural length of this part of the string, as I said, is just a third of this, because it's being split in the ratio 1 to 2. So the natural length of this part of the string for T1 is 0.5, and for T2 is just 1. And now the extensions are these here. So this string here is sitting, it should be length 0.5, as I said. In equilibrium, it sits at length 1.5. So the extension is 1, because 0.5 to 1.5, minus whatever little length x it's already going in this direction. So that's 1 minus x. And this one here, again, should be sitting at length 1, is currently sitting at length 3. So that's extension 2, plus whatever little x you've moved it over this way. So that's our formula here. We can obviously tidy this up, and we'll end up with this. Times everything by 5, we end up with this. This is simple harmonic motion with omega squared equal to 225, so makes omega 15, and we end up with our simple harmonic motion. Okay, so find the maximum speed. Maximum speed happens when you're in the middle of your simple harmonic motion, so when x is 0, you can use this formula and set x equal to 0. I like this formula. I think it's really helpful, really useful. Obviously, when x is 0, you get v squared equals omega squared, a squared, square root to get this. A, as I've said, its equilibrium is here, and it's being moved 0.5 along to start, so its amplitude is not going to be is going to be that, right? It's going to be the 0.5. Omega is 15, as I've already said, and we end up with this. Maximum acceleration. Now, its max acceleration is when you're on the end. So what we could do, there's a few ways of doing this, and what you can do is you're allowed to just use this, right? Acceleration is x double dot, and just put x equal to a, because you're on, I don't know why that's been written twice. Put x equal to a, because maximum acceleration is when your displacement is when you're on the end of the simple harmonic motion. So set x equal to 0.5. The minus doesn't really matter here, because it's just the direction, isn't it? So we can just say maximum acceleration is that. Find the total time the speed is greater than this. I think I used this formula again. You could also use this formula for the maximum acceleration, a omega squared, if you just want to remember that. That you could just use. I think I used this again for this. I did good, cool. So I want v to be 5. Omega I know is 15. A I know is 0.5. Solve for x. Eventually you get this. And now, okay, we can use this formula here because we're starting from the end of the simple harmonic motion. Right, we've moved here, and the starting point is here when t is 0. So x, firstly I'll set it as positive root 5 over 6. And times by 2, do cos inverse, divide by 15, you get this. So that's the first time. So we start here, it rebounds back, and after this many seconds, which is a very small amount, we're traveling at 5 meters per second. And now, what about the other displacement when we're minus root 5 over 6? Well, let's also solve that. And we'll find another time, which is this. And if we do this time, so that's the amount of time it takes to get from here all the way to here. And if we do that second time, minus the first, that will be the length of time it takes to get from this 5 meters per second to this 5 meters per second, which is that. But of course, in the total period, which goes from all the way to here again, you'll do that journey from here to here twice. You'll do it from here to here, and then when it comes back, you'll do it from here to here. So let's double this to get the total time in each period, that it's over 5 meters per second, and we'll get that. And I believe that is the question done. I was about to say that's the whole paper, but it's not. There's actually a question 7. So let's do that next. We have, and last, of course, we have, this is a vertical circular motion question, which you always see. The nice thing about mechanics papers, isn't it, is that you get the same questions every time. So we were expecting this to be the last question because it's always a question like this on there somewhere. So we have a rod being held horizontally, and it's projected down with speed u. And it says explain why the acceleration, and then when much later on, it comes to rest at point A. So you fire it down, and then maybe it doesn't make it all the way around. Maybe up here somewhere, it comes to instantaneous rest. And apparently the acceleration at that time, at that position, is perpendicular to OA. A, of course, being the end, and O being the center. Now, why is that? Well, of course, acceleration is given by, or acceleration towards the center is given by v squared over r, where r is the radius. But if your v is 0, if you're at rest, then that means there's no acceleration towards the center. But of course, there is still acceleration perpendicular, and if that's the only acceleration that's going on, then of course that means that the final acceleration is perpendicular, because it's the only acceleration that exists. Something like that, I think, will do. Anyway, like I said, this comes to instant rest over here somewhere. You've still got an acceleration in this kind of direction. Of course, it will be actually going the other direction, but it doesn't really matter. You've got no acceleration towards the center because you're at instantaneous rest, as we've already said. Now, we can do some energy conservation here. Apparently, it's the acceleration makes an angle of theta to the horizontal, which I then said that makes this here, because if you extend that triangle there, you get a right angle here. This is 90 minus theta, of course, and then therefore this is corresponding, so you get this. I don't know why that's helpful. I know why it's helpful, because you do conservation of energy, as I said. The only energy, if you take this to be kind of the ground, the only energy that this has in this at the start is a half mv squared, just the kinetic energy, where the speed squared is this. They've given us that. I don't know why I haven't used capital L's. That's lazy of me, but I should have used capital L's. It doesn't matter. The only energy you have at the end, you've got no velocity, right? So the only energy you have at the end is mgh, where h is L times sine of 90 minus theta. But of course, sine of 90 minus theta is the same as cos of theta, so that's just L cos theta. And that's, I mentioned that right in the first question, so that's quite a useful thing to know, and it is, because it saves you having to work out more complicated things in your picture. Anyway, so that's that. We can, of course, sort this out. Everything cancels, and you get this. And that's... Oh, then we take cos inverse, so we find this first, apparently. Fine, whatever. I think that must be in degrees, which is fine, I guess. It doesn't say I'm not allowed to work in degrees. My phone calculator must have just been in degrees at the time that I did that. Anyway, the magnitude of the acceleration of p, so that's the other thing we have to work out. So now, of course, we need to think about some forces. So we've got mg coming down here, of course. We've got, therefore, this is mg sine theta. I don't know what the easiest way of immediately figuring that out is. Which way is which? Why? How have I done that? Well, if that's theta, then we've got here. Is it just naught an angle? There, and then there. We'll pretend that it is. I'm really tired. Sorry. Let's just say this is. Well, actually, this can't be theta because that's next to it, isn't it? Is this? Oh yeah, I know what I've done. This is, if you imagine this triangle here, this is 90. So this is theta, but then of course this is 90, so this is 90 minus theta. This is next to 90 minus theta, so it's cos of 90 minus theta, which is therefore, just like we said before, therefore this is sine theta. So that's, I think, how I got that. Of course, we can now do F equals ma this way, so we have F is this, equals m times a. Of course, stuff cancels here. Sine theta, you can you can work out sine theta properly from here. I was just really lazy and put this theta into there, and we got this as our final answer. 2 significant figures because I've used g as 9.8. That's all of that done. Find, in terms of mg, the magnitude and the tension when we're at the lowest point. So this is completely different now. We're at the lowest point, and we want to know the tension in that rod there. So, okay, well, we've got... yeah, why was there no... I'm just thinking, oh, it doesn't matter. I was just thinking why I didn't consider tension in here, but it's because the acceleration is perpendicular, so it didn't match the F equals ma. Anyway, so we have tension going this way, and yeah, we're going to do another energy conservation thing here, I think, and we're also going to consider some forces. So we've got mg coming down and got tension going up, so F equals ma means this minus this is equal to the acceleration towards the center times mass, force, F equals ma. We've also got energy conservation going on over here. So I've got, to start with, I've got a half m u squared of course being this still, plus, now if we consider this to be kind of the ground, this one is the one with the potential energy, so it's a half, sorry, mgh, where h is just this distance L, so mgl, and then here we've got some speed going across, which we'll just call v, and then we've got no potential energy. So we've got this is our energy conservation. We can of course simplify that down to this. We can get v squared equals to this, which is going to be super helpful because now we can set up F equals ma with this, because we've got acceleration towards the center is v squared over r being L, so acceleration towards the center is 8/3 gl over L, which is just 8/3 g. So that's our acceleration towards the center. Set up F equals ma. This minus this equals m times this. Add mg, add those together, and we'll get our tension. And I think that is the entire paper done. Thank you for watching.